Hi, folks. Today we're going to discuss the article entitled Attention is All You Need, with Ashish Vaswani as the lead author. This is an article published in December of 2017 and has been cited over 74,000 times. This article forms the technical basis for many of today's state-of-the-art large language models, including, for example, ChatGPT-4, BERT, and a number of others. As a part of this presentation, I'm going to put a number of secondary resources in the comments that provide a more technical deep dive of this article. To begin to explain this article, I'm going to start out by talking about the difference between linear storytelling and nonlinear storytelling. So, for example, if you were going to talk about one's life from the moment they're born to when they die, say in, for example, a movie, you may do that via a linear storytelling approach. So, for example, we could say that I was born in Springfield, my parents divorced when I was 15, I went to high school in Springfield, attended college in Spokane, got my first job in Duluth. If I provided this type of linear account, we could refer to this also as a sequence model. And so aspects of the story would be that context is really expressed as a temporal sequence. So it's displayed here, basically of this temporal sequence of birth to one's first job. And another aspect of this approach is that there's a lot of details which may not be relevant to one's story. For example, the fact that one attended college in Spokane or went to high school in Springfield may be much less relevant than, say, when one's parents divorced. But the idea here that's key is this idea that really it's a linear description of one's life and of a sequence of events. In contrast to linear storytelling, there is nonlinear storytelling. An example of this would be, for example, a flashback sequence in a movie. And so the way this works is that in contrast to basically a number of linearly understood events as being impactful in defining kind of one story, you have a number of kind of discrete events that define one story. So, for example, we have the point that someone's parents divorced when they were 15, which is just different than the fact they were born in Springfield, or that they attended college in Spokane, or went to high school in Springfield, or that their first job was even in Duluth. And so the key aspect of this nonlinear storytelling is that context is really a layering of events of varying strength. And where strength is really the ability to dictate context for other events, and that this is really what's most impactful in understanding one story. And this is generally going to be kind of how the attention model works, or in that it is really kind of a non-linear approach to creating meaning and value. As previously shared, sequence models can be used to infer one's story. So, for example, you can have a sequence of events that really lead up to define who one is at a particular point in time. By analogy, the same approach can be taken with how to infer kind of the next word in a sentence. So, for example, imagine you have the sentence, it's Halloween, and all the cats are, and you have to fill in what the next word is. Well, if you kind of follow the sequence, then there's a high probability that the next word is really black. And this is kind of the approach of what are called sequence models, and was really kind of state of the art up until the publication of All You Need Is Attention back in 2017. Now, what are some challenges for sequence models used in inferring meaning? Well, if we take the previously provided sequence, namely that one was born in Springfield, the parents divorced when they were 15, etc., one of the challenges with this approach is that certain points in the sequence can have an outsized impact on defining kind of who one is, or the end result to be inferred. And so here, for example, the point of one's parents divorcing can have an outsized impact on defining who one is relative to the other, basically, points in the sequence. So the same is true with, for example, some sentence examples. So take the following sentence. It's Halloween, and even though all the cats were white, they should have been black. You would only know that the word to be inferred would be black based upon the existence of the word Halloween. But that word is expressed early on in the sentence rather than later. It may be challenging because, again, the word Halloween, much like when one's parents divorce, has an outside impact on what word should be inferred next. So this really underscores some of the challenges for sequence models, namely that certain events can have outsized impacts. So if you look at divorce or Halloween, You may have to learn extraneous details with a sequence model. So for example, high school may have little or no value in defining who one is, similarly to how the words "and even though all the" may have minimal value in inferring that the next word in the sentence ought to be black. And further, these inferences are limited by the finite nature of the sequence, namely that strong contextual elements, such as divorce or Halloween, may appear earlier on before basically the target sequence or the target to be inferred. And then lastly, meaning can be based upon non-sequential contextual elements. So for example, adjective, noun, subject, object, verb, proposition. Basically, these are non-sequential elements of a sentence. They can appear anywhere in relationships. That can appear anywhere in a sentence and are not tied necessarily to sequence. Let's take a deeper dive on intension models used to infer meaning. So an intention model, also known as a transformer model, defines a context and then uses this context to infer a meaning. So for example, the sentence, "It's Halloween, and even though all the cats are white, they should have been black." This sentence is illustrated here, shows a number of pairwise relationships between words and their relative strength, and how these pairwise relationships can be used to infer that the next word is black. Which really gets us to that for transformer models, context is to be understood as a layering of events or words of various strength that are used to infer meaning. So for example, the word Halloween and cat can be used to infer that the next word ought to be black is compared to even and all, which really don't have much strength in inferring that the next word should be black. And further, that context is to be understood as a layering that represents a distribution of word combinations, illustrating the correlative strength between each word. And we'll get more into these concepts in the next slide. So let's look at an example of doing translations using a transformer model. Imagine you have the following input and target sequence. You have the input sequence, "Die Technologie dafür ist da," and the target sequence of "the technology is there to do it." The relationship between the words in these input and target sequence can be represented as follows. You have a number of pairwise relationships where the relationships are representing the strength of the words. And so, for example, you have the relationship between ist and die, and the relationship between technology and ist. And then further, on the target sequence side, you have relationships between subsequent words in the sequence and earlier words in the sequence. You'll notice that this is the target sequence and its relationship between pairwise words is a little bit different in that it's always backward looking. And we'll get into why that's the case in some of the subsequent slides. And so basically, this input sequence and target sequence can be represented in what's called a cross-attention matrix. And a couple things about this cross-attention matrix. First, the values denote the relative strength of correlation between words. Stronger correlations mean stronger inference. The sum of the rows always equals 1 because really a row represents a distribution of values, and that these values are ultimately learned by the transformer. And so we'll spend many of the next few slides really kind of talking about how you go about building this cross-attention matrix. Shown here is the architecture for the transformer model. This architecture is comprised of two parts, an encoder part and a decoder part. This encoder-decoder approach is common to other types of generative models such as VAEs. This model is at a high level a semi-supervised learning model, which means that there's no affirmative labeling of inputs. So whereas for other types of AI approaches, such as deep learning, you may affirmatively label an input that is then learned. Here, there's no affirmative labeling. Rather, value pairs are passed in and they're learned. These value pairs may be, for example, translated sentences, question and answers, and their associated feature. And you can understand why this is advantageous for such models such as GPT-4, for example, because it's impractical to have to label large amounts of data to be learned. And learning really means an association of highly granular features and value pairs based upon the strengths of these features. Further, these encoders and decoders can be stacked to learn more fine-grained features, such as, for example, adjectives and nouns, subjects and objects, and verbs and propositions. And finally, there's this concept of positional encoding, whereas with prior sequence models, it was really a temporal sequence that was learned and that denoted the position of words. Here, there's just a unique numeric value that's fixed or associated with each one of the words in a sentence. And we'll learn about all of these concepts in the subsequent slides. Shown here is the transformer model conducting inference. The way this works is, for example, a query, such as a German language sentence, is passed into the encoder. From this query, a key value matrix or matrices are generated. These key value matrices effectively create context from which the English language sentence is inferred. These matrices are passed to the decoder, and the decoder basically starts inferring. And so at the beginning, there's kind of a number of passes that are made. So a first pass is going to be a start token denoting the beginning of the English language sentence to be inferred. The next word that is inferred is the. The next two words are the and technology, and so on until an end of sentence token is reached. So generally, this is thought of as what's called an autoregressive approach to meaning, basically meaning that the words to be inferred are based upon the previously inferred words. And this is done through what's called a cross-attention matrix that uses the key value matrices and decoder masked values to basically infer the next word in a sentence. And that this next word is selected based upon the highest probability of words, although in some cases sampling is used to select the words. And these words are selected from a dictionary of all possible words used to train the dictionary. We'll explore these concepts in detail in the next slides. This slide depicts the notion of multi-head self-attention. Prior to the creation of the transformer models, sequence models used what could be called, or what is called, such as self-attention, where basically you would take a word and determine the statistical strength between that word and all other words in the sentence. But this is typically just done once. What all you need is attention introduces is the idea of multi-head attention, where every word in a sentence and the strength of those words are compared to every other word in the sentence. And this is repeated for all combinations of word in an input or a sentence, and this is done in parallel. Whereas with the prior sequence models, there was no parallelization of this process. The parallelization of this process really sped up computing and made transformer models be able to learn much more quickly than prior sequence models. Once multi-head self-attention is performed, a score matrix is generated. This score matrix really showing the relative strength of words, or the relative correlate strength between words. So for example, here you see that the correlation between D and D is very high, whereas the correlation between D and defer is very low. And what we start doing by creating this score matrix is developing a profile of what words are more dominant or predictive of future or subsequent words in a sentence. Once the score matrix is created, it is passed to a softmax function. The softmax function then generates an attention weight matrix. The attention weight matrix basically is a matrix reflecting a normalization of the values in the score matrix. So as shown here, each row in the attention weight matrix sums up to 1, representing a distribution of inferences for word combinations. And further, this attention weight matrix denotes what words are more dominant as compared to others in inferring meaning. The product of the attention weight matrix and the score matrix is then created in the form of a value matrix. The value matrix is basically the final weighted strength of each word, understood relative to each other word. The key values and value matrix are then used to create basically key value matrices, which really are output to be used by the decoder that create context to infer a target sequence. And as a part of the key value matrices, positional encoding is also included to denote the position of each word in the input sentence. Let's move on to the decoder and the concept of masked multi-head self-attention. To understand this concept, it's necessary to understand that masking is used to ensure that the target sequence is predicted by prior words, not future words. And this is really the idea that it's autoregressive. So at this point in the decoder, a masked value matrix is generated. This matrix is generated using the methods outlined in slides 10 through 13, with the difference that future predicted words are masked relative to when they appear in the target sequence. So for example, at a first pass, maybe you pass in a start token, and there's a prediction made based upon that start token from the context of the provided key value matrices from the encoder. At the next pass, you basically mask all words after the. At the next pass, you mask all words after the and technology, and so on. And you continue this until you reach an end of sentence token. Shown here is the process to create a cross-attention matrix, namely the key value matrices from the encoder and the key masked value matrices from the decoder are combined, and a product-wise matrix in the form of a cross-attention matrix is generated, showing the relative strengths between the input sequence and the output sequence. Another way to understand masked multi-head cross-attention is with the following graphic. This graphic shows basically the layering of various relationships between words based upon strength, and where this layering of attention can be used to create richer contexts, such that you can tell the difference between, for example, the mapping between D and the, or D and the, or D and technology, or D and it. And that this graphic, which is also used in the article, Attention is All You Need, really also promotes the idea of explainability, because it's one thing to represent or state that there's a masked multi-head cross-attention matrix, or there's masked multi-head attention represented in a matrix. It's another thing to graphically represent the strengths between words, and that this graphic, for example, is much more explainable than a mere matrix. Once the cross-attention matrix is created, it provides context that is either learned or used to predict the next word in a sentence. So this learning or prediction is facilitated via a linear neural network. And as previously said, when predicting, basically predictions are based upon what the next possible word is in the sentence, plus what the prior words were in the sentence to be predicted. And this really can be represented as the probability of a target given a context. Summing it up, transformer models are a form of semi-supervised learning trained on input and output value pairs. Further, attention distributions are created and that are used to denote the strength of associations between input-output pairs. This based upon probabilities. Further, these attention distributions are learned at the feature level, which captures the inherent structures of each input and value pair. And finally, output is inferred based upon input and learned attention distributions. I hope you've enjoyed this presentation.